All right, for section 3.2, we're going to start looking at the derivative as a function. So we're going to start in with a couple examples. We're going to be focusing on this form of the derivative. So f of x, f prime of x equals f of x plus h minus f of x. Oops, all that over h, and I forgot the limit as h approaches 0 out front of that. So we create a little bit extra room, and we're going to throw limit as h approaches 0 out front. Okay, so this is the definition of the derivative we're going to be working with. In the previous section, we kind of looked at the derivative at some numbers. Here we're using kind of x as a stand-in instead of a. So we have x plus h minus f of x instead of a plus h and f of a. So we're going to look at example 1 here. And I think we're going to do kind of a probably up to about example 3 or 4, and then kind of pause on this video there. So instead of spreading it out over a bunch of little videos, we're going to do kind of a longer one. So we want to prove that f of x equals x cubed minus 12x is differentiable So I want to prove that's differentiable. We want to compute f prime of x, so we want to find an equation for the first derivative. And we want to find the equation of the tangent line at x equals 3. Okay, so first of all, if we want to prove f of x is differentiable, what we mean when we say a function is differentiable, we mean f prime of x, so the first derivative exists for all the x's where the function is defined. So what we're going to do here is we're going to prove that f prime of x, so we haven't defined what x is, we're going to let x be just a variable. We want to prove that we can figure out what this expression actually is. And then if we can figure out what that expression is in terms of x, we will have a function that we can view as our first derivative. So here's our base function here, and then we'll have a function in terms of x that'll be our first derivative. So I need to figure out what f of x plus h is. So what this says to do, we're going to do x plus h cubed minus 12 times x plus h. So this is all the stuff in this parentheses, that is f of x plus h. We're going to subtract from it f of x, which is x cubed minus 12x. And then we're going to put that all over h, and again, I forgot my limit, as h approaches 0. So to figure out x plus h cubed, we're going to use the binomial expansion. And again, if we forgot the binomial expansion, we can actually use Pascal's triangle. So I'm just going to show you this little trick here. We have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And this one right here, this is for no x. This is for x to the first power. This is for x squared. That's for x cubed. This will get me the coefficients from whenever I cube this. So I'll get 1 for x cubed. I'll get plus 3x squared h plus 3xh squared plus back to 1 here. So it's 1, 3, 3, 1. And the 1 is h cubed. And that should be our, that should be a kind of a quick little shorthand way we can generate this, use this here to generate that and do the binomial expansion for cube. So then we get a minus 12x minus 12h. We'll distribute this. We'll get minus x cubed plus 12x. All that over h, and again, I forgot to put the limit out front. So limit h approaches 0. If on the AP test, if I don't put that limit out front, then everything is wrong, basically. They don't care what you're doing at this point. It's supposed to be a limit, so it needs to have a limit out there. Minus 12x can cancel with minus 12x. X cubed can cancel with negative x cubed. And the remaining stuff doesn't really cancel. So we'll get limit h approaches 0 of 3x squared h plus 3xh squared plus h cubed minus 12h, all that over an h. So now what we'll do is we'll cancel one of the h's from everybody. So the bottom h here is going to cancel that h, cancels the square, leaves a single one behind, cancels the cube, leaves the square behind, cancels this h, and we get limit h approaches 0 of 3x squared plus 3xh plus h squared minus 12. Well, if h goes to 0, then these two terms here that have h's in it, this would be 3x times 0. So that whole term goes to 0. And this would be h squared, which if h goes to 0, something going to 0 squared still goes to 0. So those would be zeros. And we get 3x squared minus 12. So my first derivative, f prime of x, is 3x squared minus 12. So this is kind of nice because now I have a function. I can input the x. I can input the x into this function, and the output tells me the slope of the tangent line for that particular x value. So, okay, here's the first part. We did all that work. We got our derivative. So we computed f prime of x. We found its derivative. Since the derivative exists for all x, this proves that it's differentiable. And now what we need to do is find the equation of a tangent line at x equals, well, it was supposed to be negative 3. I think I wrote positive 3. So we want to find the slope of the tangent line at x equals negative 3. So the tangent line equation we're going to use, we'll use the y minus, it's going to be f of negative 3 equals f prime of negative 3 times x minus negative 3. Minus a negative is going to turn into a plus. F of negative 3, okay, let's figure that out. That's something cubed minus 12 times something, so that would be f of negative 3 would equal negative 3 cubed minus 12 times negative 3. Negative 3 cubed is negative 27. Negative 12 times negative 3 is positive 36. So I believe that equals 9. So f of negative 3 should be a 9. And then when we want to go through and figure out f prime of negative 3, we're going to plug into this equation here. So if f of negative 3 is 9, then f prime of negative 3 will be 3 times negative 3 squared minus 12. See, negative 3 squared is positive 9. 9 times 3 is 27. So this is 27 take away 12, which is 15. So f prime of negative 3 is 15. So recopying this down to get our equation of a tangent line, it's y minus 9 equals 15 times x plus 3. That should be our equation of a tangent line at x equals 3 that they asked us about. Okay, so that's first example. Got that wrapped up. Next, let's look at example 2, and this is going to want us to prove that a certain thing is differentiable, and then prove that the y prime exists, and then calculate what it is. So for example 2, we want to prove y equals x to the negative 2 is differentiable. And we want to calculate y prime. So y equals negative 2. We're basically trying to show that the difference quotient limit as h approaches 0, f of x plus h minus f of x, all that over h. We're trying to prove that that exists, that limit exists for all x except for x equals 0, because the domain of this expression here x to the negative 2. That has a vertical asymptote at 0. So domain of y equals x to the negative 2. That is, we could say, the set of all x such that x is an element of the real numbers and x is not equal to 0. So this set here is the domain of that. So we're trying to show for basically all x's that are real numbers except for 0 that the limit as h approaches 0 of, we'll write this as, I'm still going to write it as f of x plus h, I guess, even though the function thing there is y, just so it's kind of clear what we're using. We'll write it that way. And then if we can prove that this limit exists for all the x's like this, then we'll have proved that we're differentiable, and we'll have calculated y prime. So y prime will equal this sort of stuff. So y prime is going to equal f of x plus h for x to the negative 2. We want to remember x to the negative 2 is the same as 1 over x squared. So we want to kind of note that that's true. So we get 1 over x plus h squared minus 1 over x squared. That's for f of x. It's 1 over x squared. All that over h, limit as h approaches 0. So if we can show that this right here has some nice form and exists and is good, then we'll have proved that we have that the function y is differentiable, and we'll have calculated out its first derivative. So let's see here, limit as h approaches 0. So to approach this, I think we're going to need to find LCDs. So I think we need to multiply these by x squared over x squared. And I think these over here get x plus h squareds over x plus h squareds. So then we get x plus h squared times x squared. We have an x squared minus an x plus h squared, all that over an h. Okay, so I'm going to FOIL out this top part here and then distribute the negative, and I'm going to kind of save space. I'm going to kind of do that in my head. This part here is still x plus h squared times x squared. I'm going to leave that kind of as is. It's all over h, so we get an x squared. This will FOIL out as x squared plus 2xh plus h squared, but the negative will distribute, so it'll be minus x squared minus 2xh minus h squared. And let's see if anything nice happens. Okay, well, x squared and negative x squared cancel. So this kind of leftover part here is my top. I'm going to view this as h over 1 and do keep, change, flip. So we have negative 2xh minus h squared, all that over x plus h squared times x squared, all that times 1 over h. So h is now in the bottom. Both of these top terms here have at least one h in it, so I can cancel this h with that h and the square on that. And then I get limit as h approaches 0 of negative 2x minus h, all that over x plus h squared times x squared. So now if I let h go to 0, this term will go to 0, this term will go to 0, and we'll be left with negative 2x up top because the h goes to 0. We'll have an x squared because this h goes to 0 times another x squared. So this x top can cancel with one of those x's there, and we'll get negative 2 over x squared times x, which is negative 2 over x cubed. And so this right here will tell us that y prime will equal negative 2 over x cubed. As long as x isn't 0, this exists. So this exists for all x's not equal to 0, which is the same as the domain of the original function. So this proves that our function is differentiable everywhere. And here is the equation for our derivative. So everything is working out nicely so far. Okay, so we need to talk about some new notation now. So I'm going to look at notation. So we've talked about the notation of, like, say f prime of x, and this represents the derivative of f. That's just the derivative of f. If we looked at something like f prime of 2, this would be the derivative of f at x equals 2. This is called prime notation usually. We're going to learn a second notation called Leibniz notation. So in Leibniz notation, when you want to say f prime, or where you're talking about the derivative of f, we would represent that as df dx. So the derivative of f with respect to x. So f prime would be notated that way. If you want to do f prime of x, a lot of times they'll do it still as df dx. In Leibniz notation. So it's the derivative of f with respect to x, and both of these mean the same thing, derivative of f, and usually it's with respect to x. If we had something like f prime of 2, Leibniz notation, the way we notate that is kind of weird. We would do df dx evaluated at x equals 2. So if I had, say, like y prime, that would be dy dx. If I had something like, y prime of 4, that would be dy dx evaluated at x equals 4. So now we have two different notations we can use to talk about derivatives. We have kind of the prime notation here, and we have Leibniz notation over here. The AP test uses them interchangeably. So sometimes you'll have prime notation, sometimes you'll have Leibniz notation. So we're going to get a theorem. So this theorem is going to be called a power rule. Power rule. So basically, after a while, it gets annoying doing that limit as h approaches 0 to find the derivative every time. And it turns out there's some little patterns that can be found. And so the next little bit is we're going to learn, instead of going limit as h approaches 0, f of x plus h minus f of x, all that over h, and using that to find the derivative each time, we're going to learn some nice little patterns that can kind of help us out. So we'll do, power rule says for all exponents n, d dx of x to the n is equal to nx to the n minus 1. d dx says you want to take the derivative of whatever's in the parentheses. So this is kind of using Leibniz notation, saying I want to take the derivative of this type of expression here. So, kind of what does this look like? So for example, we'll kind of write it out with the ddx stuff, and then we'll kind of look at it in the prime notation method. So let's say I wanted to do ddx of x to the 5th. This would equal, by this thing here, this would be 5 times x to the 5 minus 1 is 4. So the power pulls down, and then you subtract 1 from the power. That would be your answer there. Let's say we wanted to do ddx of, x to the 3 halves. Well, 3 halves pulls down, so that's 3 halves. X, 3 halves minus 1, 1 is 2 halves, so 3 halves minus 2 halves, so that would be x to the 1 half. And that would be our answer there using the power rule. Where you see this also is you can see this in prime notation, or kind of use the prime rule. So let's say we have an example, and let's say that we have y equals x to the 2/5, and we want to find y prime. So we want to find the derivative of x to the 2/5. So by the power rule, y prime will equal, I pull the 2/5 down, So the thing I'm trying to find the derivative of is just x to a power. So I pull the power down, I subtract 1 from it. 2/5 minus 5/5 is negative 3/5. So this would be my first derivative. Okay, so that's probably enough examples to kind of see how that works. Okay, so we're going to do just a couple more things, then we'll say, we'll stop the video here, and then this will be kind of the part 1 video of section 3.2, and then I'll post the part 2 video later tomorrow afternoon. I think we're getting close to kind of where in the lecture we do face-to-face, we're probably not getting much beyond the next example or two that I put up here. Okay, so we're going to get theorem 2. This is going to be what's called linearity rules. Okay, so this is going to be linearity rules. So we're going to assume f and g are differentiable. That means f and g's derivative exists everywhere the f and g function are defined. So basically we say, all right, we're going to assume f and g. So assume f and g are differentiable. So again, this means wherever f exists, its derivative also exists, and wherever g exists, its derivative also exists. So f and g, you can take the derivative over f and g's entire domain. We get the sum and difference rule. So if f and g are differentiable, then f plus g and f minus g are differentiable. So if f and g themselves are differentiable, then when you add the two functions together, the derivative of that exists for its domain, and f minus g, the derivative of that, can be taken and exists for its domain. And furthermore, we get some expressions. If I want to take f plus g and take the derivative of the whole f plus g, it turns out that's the same as taking the derivative of f and adding the derivative of g to it. And if I want to take the entire f minus g function and take its derivative, that's the same as taking the derivative of f and subtracting the derivative of g from it. So these are kind of two rules that let us break up derivatives, which is going to come in handy. We'll use this quite a bit. And we get this constant multiple rule. So what the constant multiple rule says is for any constant c, we get c times f is differentiable. And we also get that c times f prime will equal, I can pull the c out front, it's c times the derivative of f. So these are our sum and difference rules and our constant multiple rules. And we're going to want to use these to kind of speed along the process of taking derivatives. So next example. This is example 3 in the book. We want to find points. Find points on the graph of f of t equals t cubed minus 12t plus 4, where the tangent line is horizontal. So, first of all, we need to figure out, okay, what does it mean for the tangent line to be horizontal? Well, if the tangent line is horizontal, that means the tangent line has slope 0. we remember, what tells us the slope of the tangent line? Well, the first derivative is a function that tells us the slope of the tangent line. So what this is really saying is, where does the tangent line have slope 0? F prime of t will tell me the slope of the tangent line. So I'm really asking, where is f prime of t equal to 0? Tangent line has slope. F prime of t tells me the slope of the tangent line of the function f. So I'm looking, where is the slope of the tangent line equal to 0? So I want to take the derivative of this expression here. Now, I'm going to switch over to Leibniz notation to make the next step here where I start breaking stuff up to make that a little clearer. So I want to take the derivative of t cubed minus 12t plus 4. So I'm going to go over to Leibniz notation and say I want to do d dx means I want to take the derivative with respect to, our variable here is t, so instead of d dx, it would be d dt. I want to take the derivative of the expression in the parentheses with respect to t. So I got t cubed minus 12t plus 4. So t cubed minus 12t plus 4. So I'll use this to generate the derivative, and then I'll set that derivative equation equal to 0, and that will tell me t points where the tangent line has slope 0, which will be points where the tangent line is horizontal. Okay, so we're going to use the sum and difference rule. Basically, if I'm adding two things together and then taking their derivative, that's the same as taking the derivative of the individual pieces and then adding or subtracting them together. So what that sum and difference rule is going to let me do is it's going to say I can talk about just the derivative of t cubed. I can talk about the derivative of 12t, and I can talk about the derivative of the constant 4. So instead of doing the derivative of all these things added and subtracted together, I can talk about adding the derivative of the individual parts or subtracting the derivative of individual parts, and that's equivalent to the derivative of the entire thing. Next we got this 12 times t. 12 is a constant, so we're going to use the constant multiple, and that's going to let us push that c outside of the stuff that we're taking the derivative of. So we'll get d dt of t cubed. Constant multiple says the 12 can come out front, and we'll have d dt of just t itself plus d dt of 4. So we're going to use the power rule to figure out the derivative of t cubed. The 3 comes down, so that'll be 3t squared minus 12 times the derivative of t itself. If we remember, we said if you have t itself is linear, that's an mx plus b form. There is no b, it's the m in front of t is a 1. So when you have d dt of just t itself, that's a 1. And then d dt of a constant, d dt of 4 is 0. So we end up with 3t squared minus 12. So this right here is our f prime of t. This is our derivative, the equation of our derivative. We said, okay, here's our equation of our derivative. I want to know where is that 0, because setting the derivative equal to 0 is the same as asking where are the slope of the tangent lines equal to 0. So we'll say, okay, where is 3t squared minus 12 equal to 0? So that's at 3t squared equals 12, which is at t squared equals, divide the 3 across 4. So t equals plus minus square root of 4, which is plus minus 2. So I know the x values of the point on the original function where the tangent line is 0. It's at positive 2 and it's at negative 2. So let's use that and go all the way back up here. So we have positive 2 for the x value. There's going to be some y value it pairs with, and negative 2 for the other x value, and there'll be some y value it pairs with. To get those values, I'm going to plug positive 2 into this equation here, and then negative 2 into that equation there. So let's do positive 2. 2 cubed is 8. We're going to subtract 12 times 2. Negative 12 times 2 is negative 24. So we want to do what is 8 minus 24, and that should be negative 16. And then we add 4 to it. Negative 16 plus 4 is negative 12. And so that gets us our first point that we know the tangent line has slope 0 at. So then we want to find what about, so basically what I'm putting in there is the original function of 2. Not the derivative. We use the derivative to find this value here. Then to get the corresponding y value of the point, I plugged it back into the original function. So for this one, I want to figure out what's f of negative 2. Okay, so negative 2 cubed is negative 8. Negative 12 times negative 2 is positive 24. So negative 8 plus 24 is 16. 16 plus 4 is 20, so that should be negative 2 and 20. And that wraps that example up. That's example 3 from the textbook. So I think to finish off here for this part of the notes, we're going to look at example 4, and then that should be a good stopping place. And I think in class, we're going to finish up 3.1 in class tomorrow and start 3.2. And I don't think we're going to get much beyond this example in class. And then I'll finish up, make another recording of 3.2 and post that a little bit later in the afternoon. So for example 4. We want to know what is dg dt evaluated at t equals 1, where g of t is equal to t to the negative 3 plus t to the square root, or 2 times square root of t minus t to the negative 4/5. Okay. So first we're going to calculate what is dg dt. So I want to take the derivative with respect to t of our g of x function. I'm going to put square root of t as t to the 1/2 power. Like that. There we go. Okay, my derivative operator is going to break across the sums and break across the subtractions, so I can talk about the derivatives of the individual pieces. And then this constant multiple here, this 2, is going to be able to push out front of the middle derivative. So when I apply those derivative rules that we set up a little bit above, we're going to get the derivative of t to the negative 3 plus, let the constant multiple go out front, the derivative of t to the 1/2 minus the derivative of t to the negative 4/5. So now I'll go through and actually take the derivative of this stuff. I'm going to use the power rule here, so negative 3 goes up front. Negative 3 minus 1 is negative 4. Plus 2 is out front. The 1/2 comes down. Times t to the 1/2 minus 1 is negative 1/2. Minus the negative 4/5 comes down. And then t to the negative 4/5 minus 1. Minus 1 is 5/5, so negative 4/5 take away 5/5 is negative 9/5. Let's algebraically clean this up a little bit. So this is negative 3, t to the negative 4. 2 times 1/2 cancel, so it should be plus t to the negative 1/2. Minus a negative is a positive 4/5, t to the negative 9/5. So this is my dg dt equation. It asks me to find what's my derivative. So we got our derivative, and then we need to figure out what is dg dt evaluated at 1. So I guess technically it only asked us for dg dt evaluated at t equals 1. But to get there, we had to get the dg dt equation. So what this has to do is take the derivative function and replace all the t's with 1s. So 1 to the negative 4 power is 1, so we get negative 3, plus 1 to the negative 1/2 power is 1, plus 1 to the negative 9/5 power is 1, so we get 4/5. Okay, so I need to convert, let's add these together first. Negative 3 plus 1 is negative 2, plus 4/5. Negative 2 is going to be, let's see, I need it in terms of fifths, so it's going to be negative 10/5. 10 divided by 5 is 2, plus 4/5, and then that will be negative 6/5. And we'll say that's good enough. Okay, so that should do it. That'll be like the first part of the lecture notes. The rest of the section will get up there later tomorrow afternoon.